week 9, we were tasked with implementing terrain editing to add functionality that allows a user to interactively modify the terrain, raise, lower, and flatten, and update the height map accordingly. So in the textbook version of the code, we're given this Java program that, when run, generates an OBJ file and generates this fractal terrain object file, which, as you can see, it's a bunch of numbers, and then when you open it, you get this fractal terrain. Okay, so in our implementation, now when we run this, it compiles, and we're using the lightweight Java game library to generate the same fractal map. And then here, if I let me turn on screen key. If I press the I guess it doesn't work for the mouse. Okay. So if I left click the mouse, it raises, and if I right click, it lowers. And then if I press R on my keyboard, it'll reset. So I can raise different areas and reset them. And then if I press E on my keyboard and I quit the program, it generates a OBJ file. And when I open this, which is an individual, when I open this file, our model is the one created by the program. Sweet. Okay, so let's go over the code and what it does. So all this stuff in red is, and let me kill screen key real quick. That's gonna get annoying. So all the stuff in red is what my team worked on. Let's talk about the render terrain function. Okay, so this method is responsible for rendering the terrain on the screen, and it uses OpenGL display to list the optimized rendering process, and display lists are precompiled with OpenGL, and the terrain is rendered as a grid of triangles with each vertex position determined by the height map array. This method also handles the rendering of a highlighted quadrant of the terrain, which is what was in green, and a slight offset is used to make it stand out. And if the terrain display list hasn't been created, it generates one. Let's see, generates one, and by compiling the terrain geometry into a display list, the highlighted area is rendered separately and is updated based on the mouse position. Alright, then the update highlight, which is right here. Update highlight method updates the highlighted quadrant of the terrain based on the mouse position. So when I'm hovering over, well, it's not exact, but I can use the mouse and the movement of it across the screen to dictate which square is highlighted. And it converts the mouse coordinates from the screen space to the normalized device coordinates, then maps these coordinates onto the terrain grid. I had to fudge it a little bit. I tried to get it as one-to-one as possible, but the way that window sizes work on different computers, the screens are going to be different, so it ended up just being too much hassle. Going forward, if I want to update this, I could try and implement something that would be a little more accurate. And then the method ensures that the highlighted quadrant stays within the bounds of the terrain. Okay, let's talk about the raise, lower, and reset terrain. So first is raise, and it raises the height, raise terrain, which raises the height of the terrain in the highlighted quadrant and iterates over the vertices in the highlighted area and increases their height by a fixed amount, which is the raise amount right here. After modifying the height map, it recalculates the normals for the affected area to ensure proper lighting, and then finally rebuilds a terrain to display list to reflect the changes. Lower terrain is basically the same thing, but instead of increasing the height, it decreases by a fixed amount, which is this lower amount. And then reset is copying the original height values, which are set at the set here. Where is it? Height terrain list. Original height map. Let me see. Yeah, here it is. Original height map. Okay. Back to the height map for the highlighted areas. After resetting the height map, it recalculates the normals and rebuilds the terrain display list, and it's useful for undoing any modifications made to the terrain, and it's called in later functions by pressing R. And then the export to OBJ, which is right here. This method exports the current terrain to an OBJ file, which is a common 3D model file format. It writes the vertices and faces of the terrain to the file, creating a mesh that can be imported into other 3D modeling software. It's like this 3dviewer.net. The vertices are written first, followed by the faces, which are defined as triangles. The method ensures that the exported file accurately represents the current state of the terrain. And then the calculate normals function, which is we added the vectors. So this part of the code calculates the normal vectors for each vertex in the terrain, and the normal vector you need for the lighting calculations, and the normals are calculated by taking the cross product of two vectors derived from the height differences between adjacent vertices, and the resulting normal vector is normalized to ensure it has a length of 1. And I think that's all the code, so we'll just demo it again real quick, just so you can see it working. So going forward, one thing we can do is add like a way to increase the spikiness of the fractals instead of, and when we press R, like it actually flattens. While I was building this, it was reminding me of a childhood game I used to play, Roller Coaster Tycoon 3, and the map editor that they had in there. And I had a lot of fun with that growing up. So that's our video.